Good morning, good afternoon. It's a great pleasure to me introduce Rafael Potrie. He works he's professor in CEMAT, Universidad de la República, Uruguay. Now he's in the Institute for Advanced Studies in Princeton, and he, El Gordo, will speak about foliation preserving homeomorphisms of tree manifolds.
Okay, thank you very much, and thanks for the invitation. And I don't know if you can see the screen where I will be writing. There's an option in Zoom that you can pin the camera that you want to see all the time. So if some microphones will be open, maybe it will change unless you do this. So it's better if you can do that way.
Yeah, but it's out of focus.
Let me see. The focus should be corrected by itself, hopefully. Sorry.
Now it's better.
Yeah, it's better.
Okay. So I will discuss.
I only see half of the paper.
I will be seeing what's happening. So I will try to.
I don't see everything you are trying to show.
You don't see where it says foliage?
Just there, no.
Okay, that's.
I see preserving homeos, but not the beginning.
No, that is the beginning. Oh, you don't see on the left?
No, there is a foliation I made.
No, that's it. You're
Yes.
seeing it all then. That's what we're all seeing. We're seeing everything.
that-
It says foliation preserving homeos. That's all.
I am not seeing.
Anything else.
Excuse me, I am not seeing.
Maybe you should
Excuse me,
switch
Amy,
to
but I am not
full
seeing.
screen.
You move the window inside your computer.
Yes,
I am
Like-
on full screen.
By full screen?
I am on full screen.
Yes. So that I don't know.
Is this on a cell phone or in a computer screen? Because if it's on a cell phone, perhaps changing the direction of the cell phone is enough to see everything.
I think I'm on an iPad. I have the same issue actually.
So it should happen. I will copy every leaf at some point, and I will try to change the position of the camera and as I go along. I don't know. I don't know how to solve this. Sorry. Okay, so is it okay if I start? I will try to read this, and then I will send the slides to Lorenzo. Maybe I can send them right here. So I will send the slides to everyone so that you can read them as I go on.
There is the
Okay?
problem of focus.
Yeah, that would be great.
Rafael, there is
If you
a
just share
problem
the
of
slides,
focus.
that would be amazing.
Yeah, so for the focus, I just sent the whole file scanned so that you can open it if you are in a computer. Is it there? So as I start, the focus will improve. Okay.
So just a question: do you mean you send it after the talk, or you mean now that we can use it at the same time?
You just sent it in
I
chat?
sent it
Oh,
in the
you
chat.
just. Oh, thank you very much.
Okay. So that should be okay. I will write some things, but the most important things are in the PDF. Okay. So sorry for the delay. So I will start talking. So the plan I have is to explain some aspects of some joint works with Thomas Barthelme, Sergio Fenley, and Stephen Frankel that have to do with foliation preserving homeomorphisms of tree manifolds. So it's somewhat the the motivation of the work comes afterwards. I will explain it later, but first I want to just present one simple result about foliation preserving homeomorphisms. So I will work in hyperbolic tree manifolds, and this means that C2 is not a subgroup of the fundamental group of M, so M is a closed tree manifold. C2 is not a subgroup of pi1, and then pi2 of M by 3 of M equals 0. So the results I will talk about are topological. So what we really care about is these two properties that we know by like Perelman's work, that this implies that M is H3 over a subgroup of isometries. And I will consider a minimal foliation in the tree manifold, and I want to study homeomorphisms that preserve this foliation. So it's like a somewhat generalization of studying homeomorphisms of surfaces. So if you were in Mathilde's talk a couple of weeks ago, it's a similar setting. So you have a dynamics that preserves a foliation. So now the surfaces you are considering are non-compact, and there's a one parameter family of these surfaces, and the dynamics permutes these leaves and has a dynamics there. But you will use the global compactness of M and the transverse geometry to try to understand this homeomorphism. So that's the setup. And the result I want to describe first is this proposition I wrote here. I don't know if you can read it correctly, but it says that if I have a homeomorphism of a hyperbolic tree manifold that preserves a minimal foliation, then essentially either every leaf is fixed by this lift, or you have some information on the foliation, and F acts as a translation in the space of leaves.
You want the last one?
Yes.
Okay, good job.
Okay, so maybe a good idea is to close the microphone of that are open. So, and okay, so let me say some words if this statement is clear. So the first comment. So this result holds in more generality. I will stick to here, and one of the crucial things of working in a hyperbolic manifold is that F to the K for some K is homotopic to the identity. So I will assume F homotopic to the identity, and this means that I can choose a lift. So the lift in the proposition F tilde will have two properties. It will commute with deck transformations, and it will be bounded distance from the identity. Okay, so such a lift can be obtained just by considering the lift of the homotopy to the identity, and it will have these two properties. And so the first part of the talk, I will try to explain a proof of this theorem. And so let me, before I start, make a comment on the hypothesis of the foliation being minimal. Okay, so F foliation. So this means it's a partition by surfaces which locally look like this. And in particular, the minimality assumption means that every one of the surfaces in the partition is dense in the manifold. And one important consequence of this, there are two important consequences. So the first one is via what's called Novikov's theorem. Implies that in the universal cover, I'm going there. In the universal cover, every leaf separates into half spaces. This I will come back. And the second consequence I'm interested in is that there's a curve from S1 to M transverse to the foliation and intersecting every leaf. Okay, so these are the two important things I will use about this hypothesis, that the foliation is minimal. And so now I will start with the proof of this proposition, which is the first thing I want to do. And I have here some of the steps in the proof, and let me explain them a little bit. Okay, so the first point here is that once for every leaf in the universal cover, you know that the leaf separates the universal cover in here, the universal cover in two connected components, and they are oriented because we are in the universal cover. So we call them L plus and L minus. And the minimality assumption allows us to show that in every one of these half spaces, there are arbitrarily large balls inside. So the half spaces are not small. So let me make a drawing of what could go wrong. So if you have not experience with foliations, you could have some leaves like this. And here, a leaf like that, this would be L plus. And this region here would not have a very big ball inside, okay? But whenever you have a minimal foliation, this will be true. And so let me tell you very briefly, why is this true? So so idea of one. So cover a ball, any ball, by foliation boxes. And so since in the universal cover, the space of leaves is each leaf separates into components, you have kind of an orientation induced in the space of leaves. And you will find at least one leaf L0. So if the ball were something like this, then of course these leaves over here won't let the ball in this region, but this leaf here will. So essentially that's what I'm trying to say. There exists a leaf L0 such that B0 is contained in L0 plus. And then the point is to use this transverse curve to show that behind L0, you have a lift gamma of the leaf you were looking using the curve eta that will still leave the ball up in the upper region. And this is how you show that every leaf separates in two very big spaces. Okay, so that's the first point. Then we consider this lift that I mentioned, which is just lifting the homotopy to the identity. And the fact that the balls are very big in each space, so you have L here. Let me throw this page. So you have L here, and you have a ball here which is much larger than the distance from F to the identity. So the image by F of the leaf, a priori you don't know, but you know that the ball cannot separate so much. And so the leaf, this would be F tilde of B. So the leaf must be what we call nested with L. Okay, so they are like connected. And of course, you can also deduce that the space between L and L prime cannot have things like this. So it's what we call trivially foliated in the middle. Okay, so that's the second remark in the proof. And this is a very important remark because we want to show that the space of leaves which are fixed by the leaf to the universal cover is a closed and pi1 invariant set. And so pi1 invariance is very easy because of the commutation property between F tilde and the transformation. So you cannot automatically check that when you translate a leaf and the leaf is fixed, then the translate is also fixed. But the fact that it's closed is not obvious because the leaf space may not be Hausdorff. And here I draw a possible bad case. So it could be that all these leaves, which are in violet, are fixed, but points are moved a lot. And so in the limit, you get different leaves that are being translated. But of course, this cannot be true if the image of a leaf is nested with itself. So this property of having very big balls allows us to show that the space of fixed leaves is a closed and pi1 invariant set. And so either it's everything or it's empty. Okay, and remember that we wanted to show that, let me hit here, either every leaf was fixed or no leaf was fixed. So F tilde was a translation. So what's remaining to show is that in the case where no leaf is fixed, then the space of leaves is homeomorphic to R. And that's essentially because of this observation. So between L and F tilde of L, you have an interval worth of leaves. And as you start iterating, you can show that you will cover all the universal cover, because if that limits somewhere, you would get some fixed leaf. Okay, so that was the sketch of the proof of the proposition, and this is the end of the introduction to the talk, and it gives us this result here. Okay. So now I want to continue. I want to explain how we can use a result like this. But before, let me comment something to keep the relationship with surface dynamics. So in this case one, where every leaf is fixed by F tilde, you should think as the dynamics in each leaf is homotopic to the identity. Okay, so in surface dynamics, you typically separate the study depending on the isotopy class of the homeomorphism. And the case where every leaf is fixed by the leaf should be understood as the homotopic to the identity case. The differences have to do with the fact that the surface is not compact, so you have less deck transformation to play with, but you will expect to gain some information from the compactness of the tree manifold where the leaves are. And the second case, it's not so clear, and I will try to explain this a little bit later. You should think of it as the case where you are homotopic to a pseudo-anosov map. Okay, so that's just like a cryptic sentence that I will try to explain later. So before I continue, let me give you some examples of minimal foliations in hyperbolic tree manifolds and homeomorphism preserving this foliation. So a priori, at least for me, when I started thinking about this, the non-emptiness of of this was not obvious. And later I learned that there are many kinds of foliations and homeomorphism preserving them in hyperbolic tree manifolds, but I will restrict to a particular class, which is quite particular, but it's the one I'm interested in. So let me show you here. So the main example I will be interested in about minimal foliation in hyperbolic manifolds comes from anosov flows in hyperbolic tree manifolds. So anosov flows in hyperbolic tree manifolds are known to exist since the 80s by the work of Goodman. But then Fenley studied and understood that these examples could have two quite different behaviors depending on the leaf space in the universal cover. So there are both R-covered examples, meaning that the leaf space in the universal cover is homeomorphic to R, and there are non-R-covered examples where the leaf looks more like these red components I drew before. Then just let me mention in particular this Bowden-Mann's example. I think Mann will speak about this in particular in this seminar later. And it's very interesting because even in a given hyperbolic manifold, you could have several of these anosov foliations. Okay? So, and of course, if you have an anosov flow in a hyperbolic tree manifold, you have one natural dynamics and natural homeomorphism that will preserve the foliation, which is moving along the flow. So let me introduce one definition. So I'm calling here a discretized anosov flow to a flow which if you fix an anosov flow, you will take a homeomorphism which is moving along the flow a variable amount of time. Okay, this is tau of x. I don't know if it's clear. So to every point x in the manifold, I will flow some time that depends on the point. And to these things, I call discretized anosov flow. But in general, there are other homeomorphisms of tree manifolds supporting anosov flows that preserve the foliations. In fact, anosov flows come with two foliations, and there are homeomorphisms that preserve both of them at the same time and are called self-orbit equivalences. And we will say that a self-orbit equivalences are equivalent if they differ by a discretized anosov flow. So we would like to say that this kind of map, which is certainly preserving all the orbits of the flow, is a trivial self-orbit equivalence. It's not permuting the leaves. But there are other ones. And in particular, since we are in hyperbolic manifold, let me tell you which ones are the ones we are interested in. And let me explain how this is consistent with the result we discussed at the beginning. So if you have an anosov flow, which is R-covered in a hyperbolic tree manifold, then there are non-trivial self-orbit equivalents. So here I draw a way to see this. I don't know if this is, I need to explain this drawing. So here I'm drawing in red the weak stable foliation of the anosov flow and in the universal cover, and in green the weak and stable foliation. So the fact that it's R-covered means that the space of leaves is a trivial foliation of the universal cover, and I'm removing the flow direction. Okay? This is what's called the orbit space of the flow, and it's known to be always homeomorphic to a plane. And what's also known is that except for what's called suspension anosov flows, if the anosov flow is R-covered, then the space of leaves, when you look at the foliations induced in the orbit space, they look like this. It's called a skewed anosov flow. And this allows you to take one point, which belongs to a certain weak and stable and a weak stable leaf, and determine which is the orbit you will send it to. Okay, so you look at the last weak stable leaf that intersects the weak and stable leaf of X, and you do the same with the stable, and then you get a new orbit. And of course, this is a homeomorphism in the space of orbits. You need to promote it to a homeomorphism of the manifold, but that's something that's well understood. And in fact, Barthelme and Gogolev show that essentially this map generates the space of self-orbit equivalences in hyperbolic tree manifolds. And I said this is related to the proposition I mentioned, because in particular, if the Anosov flow is non-R-covered, our proposition tells you that a self-orbit equivalence in a hyperbolic manifold, at least up to an iterate, must fix every leaf and be trivial. Okay, so in order to create a non-trivial self-orbit equivalence, you need the foliations to be simple like this. Okay. Okay, and why did we get interested in these things? Is because we were trying to understand the structure of partially hyperbolic diffeomorphisms in tree manifolds. So I included here the definition, and these are objects that I won't motivate today, but on which some things very close to foliations appear naturally, and this preserve this foliation, it's natural to try to understand in general these things. And here, and one important thing I want to point out is that, as in the Anosov flow case, we have not one but two foliations to work with, and this allows us to get more information than just studying foliation preserving homeomorphisms. So if I have time, I will come back to the foliation preserving homeomorphisms after I mention some of the results I want to present. And okay, so it's I left the definition. I didn't comment on the definition of partial hyperbolicity, but it's a diffeomorphism of the manifold, and you preserve three bundles. So in general, both the stable and the unstable bundles integrate into foliations. The center direction does not always integrate into a foliation. In general, it doesn't, but at least it's one-dimensional. So you can integrate curves tangent to it, and it's a very important tool that was developed by Burago Ivanov, allows you to get things which are close to being foliation. They are not the same, but in some aspects they behave similar. Okay, so, but the fact that the center foliation does not integrate is a serious issue and a real issue. And so we need to, if we want to classify or understand topologically these systems, we need to produce classes of systems that take into account the fact that the center may not be integrable. Okay, so the classical theory by Hirsch-Puig-Schub starts by assuming that you have a center foliation. But if you change and you start with a partially hyperbolic diffeomorphism, you cannot assume that to start with. So we propose a class of partially hyperbolic systems that I will comment here, that we call collapsed Anosov flows. I don't know if this can be seen, which tries to take into account this potential issue. Okay, so we say that a partially hyperbolic diffeomorphism is a collapsed Anosov flow if there exists a topological Anosov flow in the manifold, a self-orbit equivalence, remember this was just a permutation of orbits of the Anosov flow, and a continuous map homotopic to the identity, which maps orbits of the flow to curves tangent to the center direction, and such that you see the dynamics of this self-orbit equivalence in the dynamics of F. So it's a semi-conjugacy. So H may collapse things, but the collapsing is rather controlled. So let me make a drawing of what could happen. So you could have like one flow line here and another flow line here. And the map H could do something like this. So this is like H. But so it could collapse the curves, but at least it will describe you a large part of the curves tangent to the central direction. And you can recover information from the dynamics by using the knowledge you may have about the dynamics of the self-orbit equivalence. Okay, so this, I made a remark here. If H is a homeomorphism, then this is exactly like leaf conjugacy in Hirsch-Kirchhoff, but in general, we cannot expect that. And so we allow H to collapse some of the orbits of the anosov flow. And a question that could be a way to attack the classification of partially hyperbolic diffeomorphism in trimanifold is whether every partially hyperbolic diffeomorphism in a sufficiently large trimanifold has to have this structure. Okay, so I'm here in this comment here. I'm like putting aside a lot of very interesting work that I don't have time to comment because it's not in what I'm trying to talk about today. But if the manifold is big enough, so the fundamental group is non-virtually solvable, we don't know examples which are not in this class. And so recently with Barthelme and Fenley, we show that all the examples we know do belong to this class. And this class is an open and closed class in the space of partially hyperbolic diffeomorphism. So it could be, in principle, that every partially hyperbolic diffeomorphism belongs to this class, or it could be that they don't, and so new things need to be understood. And another comment is that implicitly in the definition of a collapsed anosov flow, you have this topological obstruction thing. So if it's true that every partially hyperbolic diffeomorphism in a trim manifold with non-virtually solvable fundamental group is a collapsed anosov flow, then that would mean that if a manifold admits a partially hyperbolic diffeomorphism, then it admits an anosov flow. Okay, and that's already an interesting question. And so I want to announce one result in this direction, which like stands on the first and the starting point for the result is the proposition I started with. And it's this result that's saying that this is actually true in hyperbolic trim manifolds. Okay, so if you have a partially hyperbolic diffeomorphism in a hyperbolic trim manifold, then it has to be a collapsed anosov flow. Then I added something, but now I don't want to talk about that. But in particular, hyperbolic trim manifolds that admit partially hyperbolic diffeomorphisms admit anosov flows. So here I haven't been so strict about topological anosov and anosov flow. So in the transitive case, Shannon has shown that topological anosov flow implies anosov flow. So and in general, we at least in hyperbolic trim manifolds, every topological anosov flow is transitive. And so in the rest of the time I have in the talk, I would like to bring us back to foliation preserving homeomorphism and try to say something about how to attack this problem. Okay, so let me come back to the proposition we stated at first. So let's forget. So assume everything orientable and iterates if you want. So okay, so some of these things are not trivial to remove, but I think it's okay if we assume this. And the point is that under these conditions, we have these objects I briefly mentioned before, which are resemble foliations, but they could have some merging. And this proposition kind of gives us three cases. So case one, you have this, like, I'm calling this WCS and WCU are what's called branching foliation. So the proposition we stated at the beginning works in this setting too. And so we have essentially three cases. F tilde, so let F tilde be the good lift, as I mentioned before. And F tilde could preserve, fix both pairs of foliation. And so in this case, we want to show that F is a discretized Anderson flow. And that's what we do in this work with Barthelemy, Fenley, and Frankel. And in fact, we do better. We just need to show that if preserves fixes one of the two, so say it fixes this one, but not, then impossible. So we show this is impossible. And in fact, yeah, I'm cheating a bit because in the proposition I assume minimality, but okay, let's assume also that foliations are branching foliations are minimal. And so the point is that we are left with one case that we didn't study in this work, which is where F tilde translates both foliations, but and this implies that they are covered and uniform. And so, and the goal here is to show and to produce this structure here, to show that these two foliations, if F tilde translates both, then these two foliations have exactly this structure. Okay, and in principle, so we only know it translates. We don't know how one behaves with respect to the other. And in principle, we have these two foliations, but if these foliations come from an anosov flow, to mention one property, then every leaf should be a plane or a cylinder. So here we need to use this translation structure to see if we can get something. And essentially, so the strategy is to use some of the geometry of the foliation itself. So every leaf of is Gromov hyperbolic. And essentially, we want to show that every center leaf in the universal cover, so the intersection of a leaf of this and a leaf of this, it's a quasi-geodesic and here you see already a very strong difference with the compact, let's say, homeomorphisms of surfaces in general. So here now we have a foliation which is preserved by this diffeomorphism and which is subfoliated by a one-dimensional foliation. So that already cannot happen for higher genus surfaces because they don't admit one-dimensional foliations. Here they do because leaves are non-compact, and so you can have this. But also, if you look in a compact surface, just the fact that it's compact, you know that if you have a curve, an immersed curve that doesn't auto-intersect, then it has to have limit points in the boundary at infinity, just because you are in a compact surface. But here we cannot do that. We could use somewhat the transverse direction, but it's more complicated. So what we'll try to do is try to use the transverse geometry of M to produce some information in the leaves. So in the rest of the talk, all I will talk about is how to show that center curves inside CS leaves or CU leaves have landing points at infinity. So essentially, it's each center curve is in the universal cover is an embedding a proper embedding of minus infinity plus infinity. And I want to show that if I compactify the CS leaf, I can extend this to the boundary. So essentially, I want to show that this kind of thing is not possible. So that the limit in the boundary, it's just a point. So let me go there. And this is again a result about foliation preserving homeomorphisms of hyperbolic tree manifold. So I will have a homeomorphism that preserves a hyperbolic tree manifold, that preserves a minimal foliation in a hyperbolic tree manifold, but now I will assume that the minimal foliation is subfoliated by a one-dimensional foliation. And I will assume that F tilde is a translation in the leaf space of F tilde, which is the case, as I tried to explain, the case we are interested in. And what I want to try to convince you is that every leaf of this foliation has to have a landing point at infinity. Okay, and this in blue is what I just kind of mentioned. So there's this result by Candle that allows to put a negatively curved metric in each leaf of the foliation. And so, and this allows you to compactify each of the leaves with a circle at infinity. And showing that the leaves have landing means that you can extend them to this closure, okay? But recall that when you compactify like this, as you go to infinity, this is bigger and bigger. So in principle, there's no reason such behavior cannot happen. And moreover, notice that even if you have this foliation, the foliation is continuous. You only know that compact parts vary continuously as you move the leaves, but in the closure, they can do whatever. So you don't have control. So you would have control if you know that it's a quasi-geodesic foliation, but that's exactly what we need to show in order to get a result. And so what do I mean by using the transverse geometry? And I mean using this theorem due to Thurston and then improved by Caligari and Fenley, which tells you that whenever you have an R-covered uniform foliation, which is the setting we're in. So the leaf spaces are, and the pairs of leaves are bounded distance from each other. Then there's a pseudo-anosov flow in the manifold that it's transverse and regulating for the foliation. Regulating means that if you take two leaves in the universal cover, the time you need to go from one leaf to the other is bounded. So let me draw this and how we will try to use it. So this is L, say. This is F tilde of L. And you have this pseudo-anosov flow. You have a point X here. It goes somewhere here. So this may be phi T of X. And you push it until you touch this foliation. But it's important that this time you need to go from one leaf to the other is bounded below and above. And then you have like other orbits. Like it's a pseudo-anosov flow, so you have like a stable lamination and unstable lamination. So you have some points close by here that move over here by the flow. Similarly, you have the opposite behavior. Let's say we are in what's called a regular orbit. But then we also know that F tilde is bounded distance from the identity. So essentially, and the flow here is also bounded distance from the identity. So we know that the image of the point X has to belong here. So this is F tilde of X belongs to this neighborhood here. And F tilde of a point here, so not exactly this point because you can switch, but some point here will map over here. So if you look far apart, you get some coarse contraction and expansion. And so this becomes a tool like the same kind of tool as what's Nielsen-Thurston classification of surfaces. So now instead of having the universal cover of a surface and a map homotopic to a pseudo-anosov, you have two hyperbolic disks and a map from one to the other, which is close to something which has the behavior of a pseudo-anosov map. And this, so heuristically, this will allow you to do essentially the same things as you do with the global shadowing kind of arguments in pseudo-anosov dynamics. And so let me try to explain the idea for the proof of this proposition. Let me take this out. And the idea is as follows. So assume you have a leaf that's not landing in a point, so it will land in an interval. So now you need to use the pseudo-anosov property where you know that you have like a dense set of periodic orbits which are regular, and that way you can find like some periodic orbit of the pseudo-anosov flow which will have a behavior like this. And like this, I mean, it has at infinity you have two repelling points like this and two attracting points. And the important thing is that the two attracting points and one of the repelling points lie in the interval where the leaf is accumulating. Why is that? Because so here, as you go to infinity, you're allowed to make zigzags. But in a compact part, you cannot do so many zigzags because you are a foliation. So the leaves are properly embedded. So once you have this, you will iterate by the dynamics, and you will get that the foliation is pushed into a compact part, because the boundaries are getting attracted to these attracting points, and in the repelling point, you are pushing to a compact part. And so in this compact part, you get a figure where the foliation is like coming and going in the different orientations as many times as you want in a bounded neighborhood. And of course, this is a contradiction, and this proves this proposition. And so I think I will end here. So thank you very much, and I'm open to questions.
Any other question for Rafael?
Yes?
Nobody has questions.
Can we still ask questions?
Yeah.
Is it still open? So the first thing you said is that you're going to get a hyperbolic manifold, and so it's got a lattice, and so you're going to have an automorphism that preserves the foliation. But do you know what that means in terms of its how it acts with respect to the lattice? If it's not isotopic to the identity, is it like something centralizing the lattice?
Okay, sorry. So this I went very quickly, but since it's a hyperbolic manifold, so up to a finite iterate, you fix the lattice. So it's it's like most of rigidity, but you can do it only with the topological.
Okay. So you gain nothing by looking at the algebraic issues. It's all geometric.
Well, it's kind of, instead of having some isotopy class, you see the isotopy class by how you translate the foliation.
Right.
So essentially, that's the point.
I have a question.
Yeah.
So you're using as a as a black box, I guess, the Virago-Ivanov theorem. But beyond that, there's not much partial hyperbolicity that's being used. Is that true?
Well,
in other
this
words,
part,
this gives a much broader classification, doesn't it, than just partially hyperbolic?
Well, so the two results I explained are like partially hyperbolic free. So then I explained this theorem. I mentioned this theorem, and here we need to use partial hyperbolicity at several points, because one thing is to show that leaves land in a point, but then we need to promote that to quasi-geodesics in every leaf. And quasi-geodesics, that in general, it's not true. You can certainly blow up like self-orbit equivalences and stuff like that. So to exclude that behavior, we need to start looking at the visual measure of the landing. And that when we start doing that, we start needing to use like the stable and the center foliation, and it's a bit more delicate. So,
but have
for
in some sense
these results are general.
A broader class. I mean, the CAF, you could relax the requirement that H be C1. I'm just thinking that, in terms of like a natural class of global dynamics, not necessarily C1 dynamics.
Yeah, so this C1 along orbits is essentially what you want is that, because, okay, so this is defined for partially hyperbolic, and so we want to relate the orbits of the flow with the center direction. If we don't do that, it's a bit complicated. But I think one motivating thing for me about this project is that I understood this like self-orbit equivalence as a worth class of systems to understand their dynamics. And that was already started by this work I mentioned by Barthelme and Gogolev. And still you get many other things to say. And yeah, you can relax or not relax. It depends on how often you will find them. I didn't talk about any motivation in particular, but yeah, some of the techniques could be used in other settings.
Sorry, I have a question. What happens if you relax the condition, for instance, to have a C alpha deep field with alpha less than 1? You can, yes, there. You can recover something, or this is maybe a silly question. I don't know.
Yeah, no. So in fact, so the you mean F or
no, the H.
Yeah. So H is not a deep field. H is only continuous and homotopic to the identity. And it's only C1 along the orbits of the flow.
Okay.
And you could like eliminate this, but then you can improve. So the H is not like uniquely defined because you can change H and beta a little bit, and you can always construct from an H, which is continuous, a smoother one. You can like integrate and smooth. This is like orbit equivalence of an nozzle flows. You can always improve along the flow direction, the regularity. It's you have kind of a trade-off. You may lose regularity of beta, but that's not. In general, beta is not smooth, so it's only Holder.
Okay.
So yeah.
Thank you.
Are there more questions?
Oculing le barro de ella. Yo conozco a esa muchacha, ella se llama Nancy.
Okay, if there are no more questions, we can thank Rafael.